Welcome back to Lecture 12 in GRA 6036. We have been doing exercise 1.5 from the more math exercises, some are exercise set on p-values, and now we'll talk about interaction terms. So usually you are presented, for example, when you're given a model with an interaction term, it typically looks something, it might look something like this. So you say, well, y is beta 0, beta 1, xi plus beta 2, xi, say zi plus noise for I from 1 till n, where let's say ci is an indicator taking the value 0 for group 0 and 1 for group 1, while x is a continuous variable, for example. So you're given this model. So one thing that is nice practice to understand what this model means is to write it down as two models. So one model for the group 0, one model for group 1, because that is in fact what's going on here. There are two models, they do have something in common, but they are two different models. So let us, for simplicity, assume that zi is equal to 0 for I from 1 till m, while it's equal to 1 for I equals m plus 1 up to n. So this means that the m first observations are the group 0 observations, and the n minus m last observations are the group 1 observations. Okay, so then now we can write this model as yi equals beta 0 plus beta 1 xi, and let's say that now the i's are for the group 0, so now zi is 0, so then it is on the plus noise I for I 1 to m, and then we have beta for the group 1, we have this model beta 1 plus xi plus beta 2 xi times xi. The zi is only 1 now, so you can take the zi away, plus noise I for I equals m plus 1 up to n. And this, of course, is equal to beta 0, beta 1 plus beta 2 xi. So now we've written this model as a model for group 0 and as a model for group 1, and that makes it easier to see the difference between the two models. And it might be even easier if, because since beta 2 can be whatever, so we can write this as a new parameter if we want. So we can even write this as, let's write it as for group 0. We have y equals beta 0 plus beta 1 xi plus noise. And then for group 1, we have yi plus beta 0 plus, let's say, theta xi plus noise. And the reason, for playing around with the symbols like this is to make clear what these models, what our model for group 0 and our model for group 1 have in common and how they differ. So here we see that in this model we are forcing the intercept to be the same for both groups. So that means that if we draw our x, y, they will both intersect the y-axis, in the same place. They're forced to. That's how we build our model. But their slope can differ. So maybe beta 1 is a positive number, and maybe theta is a smaller positive number. Okay, we don't know it. These are parameters we have to estimate, but to understand, I mean, what we mean, what our intention is when we put up a model with interaction terms, you should, to properly interpret these models, write them out as the two different models that they are. Okay. So let's start in the and I mean, now we went from this model to these two models. So suppose now that suppose that instead we have two groups. We have a group 0. So we have a group 0, and the model for group 0 is yi beta 0 plus beta 1 xi plus beta 2 xi squared plus noise, while the model for group 1 is yi plus a0 plus a1 xi plus a2 xi squared plus noise. Okay, so now we have, and then we say, okay, so let's say that to make things simpler for ourselves, let's assume that I as above from 1 to m is group 0, while I from m plus 1 to n is group 1. Okay, so now we clearly have two different models for group 0 and group 1, and let's say that so now I'll go to the next page. So this is page 4. We should keep that model here. Here we are. Okay. So let's say that we think that, for some reason we think that both of these groups intersect the y-axis in the same place. Okay, well, that means that we think that a0 is equal to beta 0. Let's say that we believe that the effect of the squared term here is the same for both groups. Okay, so then we think that a2 is equal to beta 2, but we might want to test whether this slope beta 1 beta a1, we suspect that those differ, so we would like to test whether beta 1 is equal to a1. So then our typical null hypothesis then is that beta 1 is equal to a1, while the alternative hypothesis is that beta 1 and a1 are not equal. And now we want, well, so that's nice. So basically here we are, if you put all this together, I mean our null hypothesis is basically that group 0 and group 1, well, that they come from the same population, that they are data from the same underlying model, versus the alternative hypothesis that they are from two different populations, where it's only this term that differs between the group 0 population and the group 1 population. Okay, so and we want to use the functionality we know in R to test this hypothesis, so we want to use the LM function. Okay. So let's try then, since we know how to fit models with interaction terms in R, we would like to write this model as a model with interaction terms. So here we are. So to do that, we can introduce a new variable, and that you can make a new variable in R. So let's introduce our variable z again, which is the indicator for the group. So this takes the value 0 if I is equal to up to m, and 1 for m plus 1 up to n. Okay, so here we created a new an indicator. So to do that in, an easy way to do that in R is to use the rep function. So there's a function in R called rep, which is like this. So if you write rep 0, 5, it will give you 5 zeros. So this will create a vector of 5 zeros. Okay, so if you then want a vector with 5 zeros and then 5 ones, that is in the case where n is equal to 10 and m is equal to 5, to create your z, then you could do z rep 0, 5, rep 1, 5. Okay, so now that was some R stuff, but let's write down this model as a model with interaction terms. So then we can write z yi is equal to beta 0 plus beta 1 xi plus beta 2 xi squared plus, let's say, theta xi zi plus some noise, and this is then for all the observations. Okay, because now you see that this model you can fit. Now this model is on the form that we are used to. Maybe it's easier if you write it beta 0 plus beta 1 xi plus theta xi zi plus beta 2 xi squared plus noise. Well, that was you couldn't see, but I wrote beta 0 plus beta 1 plus theta times xi times the indicator plus beta 2 times xi squared plus noise, which is a squared term here. So now you see that this model is on the usual interaction term form, and if we now have our data, so now the regression data that we are to use in R is of the form x1, y1, z1 up to xn, yn, zn. So now you see that you can fit this model using the LM function in R. And then the parameter you'll be interested in for testing, remember the hypothesis. So the null hypothesis was that, well, in terms of the symbols we used up here, the null hypothesis was that beta 1 equals A1. That was when we formulated the model like this. And now for beta 1 equals A1, when we translate that to our new formulation of the model, then age 0, the null hypothesis is that theta is equal to 0 versus the alternative that theta does not equal 0. And this hypothesis is what the p-values you read out of the LM function, the LM object, when you fit this model in our tests. So this means that if you read off the p-value here, and if your p-value is smaller than a chosen significance level, then you reject the null hypothesis. If your p-value is bigger than your chosen significance level, you do not reject the null hypothesis, and then you continue to believe that group 0 and group 1 are one and the same group. There is no difference between the two groups. So the moral of this story is that each time you are given a model with interaction terms, write it down as two models, because we only in this course only look at interaction terms with binary variables. And if you are given two different models for two groups and some hypothesis, try to translate it into a model with interaction terms so that you can use the LM function to test your hypothesis.